Alright, so this brings us to laser hazard analysis number 2. Let's go to our PDB. And whoa, it's going to be a CO2 laser, a 106. Let's highlight this record and load it into the interface. Load parameters from PDB record. Alright, we have it loaded. This is a 2 kilowatt CO2 continuous wave. This is a typical power level for large CO2 cutters. Large CO2 cutters, we look at them ranging from, say, 500 watts up to multi-kilowatts. That's a fairly large CO2 cutter. Below 500 watts, whether it be a fiber or CO2, we start looking at that more as a medium powered cutting system. Let's take a look at some of the important points here. 106 micron continuous wave, 2000 watts. Notice that the ANSI exposure duration is 10 seconds. All right. We'll discuss where these defaults come from a little later on in the course. The ocular MPE is 0.1 watts per square centimeter. That's 100 milliwatts per square centimeter. So you can see that this laser, in terms of MPE, is not as hazardous of a wavelength. Okay, we'll discuss that a little later in the course, but basically it has to do with what absorber is in play for our tissue. The beam characteristics, we have an 18 millimeter beam diameter, 1.5 milliradian beam divergence. That gives us an m squared limit of 2. Again, we have the observer range set at 0, but here's the interesting point about this. Notice that even though the observer range is set at 0, which would be the smallest part of the beam or at the beam waist, we only have an OD value of 4.18 as compared to the worst case, which is 5.3. Right. Quickly mention NOHD is 1504. 1504 meters. Okay, so let's get back to what causes this. Well, look how large the beam diameter is. It's 18 millimeters. Let's look at our limiting aperture. Our limiting aperture for the far infrared, 10.6 microns, is 3.5 millimeters. So there's no way an 18 millimeter beam diameter fits cleanly through a 3.5 millimeter diameter aperture. As a matter of fact, in this situation, only 7.28% of the beam is passing through the limiting aperture. So that's the reason the OD value is down. The OD at observer range is a real world value. The worst case is somehow magically all the power passed through the limiting aperture, and this would be worst case if that were to happen. So your OD value would never exceed 5.3. In this case, we would go to OD 6. Now, what would I do here? I see that I only need an OD 5. Worst case would be OD 6. Well, it turns out for a CO2 that the eyewear is clear. So why not just pick the worst case, go with OD 6? And that's typically what we do in industrial situations. Again, let me look at the average radiance in the limiting aperture. That is with only 7.3% of the power passing. And we can see, geez, it's 1,500 watts per square centimeter. That's considerably more than our MPE, and that's the reason we have such a large OD value. One quick thing before we leave here. Oh, two more things, actually. Let me look at this. Skin MPE. Notice that the skin MPE is the same as the ocular or eye MPE. That's because the same absorber is in play. All right. So what I'd like to also know here is, well, what is the skin MPE? Well, see how this label is in a different background color. It's blue. Anywhere that I have those, I can click those and something happens. So let me click this one, and I go to the skin hazard distance, the nominal skin hazard distance. I see it's the same thing, 1,500 meters. Well, that makes sense. Same absorber, same thing's going to happen to the tissue. The ocular and skin MPEs are the same. The NOHD should equal or be very close to the NSHD. All right. Last thing I want to point out is we have the point source or the diffuse reflection NHC is 0.8 meters, right? And notice something here that this is based off of 600 seconds. We'll want to take a look at that a little closer in a couple of examples. But what happens if I change that to 10? Does anything change? No, it doesn't. So we'll have to look into the tables as to why, if I change this exposure duration, nothing changes. Let me put that back to 600, and let me try 600 over here, and yeah, nothing changes. So this will give us something to look at that we'll need to investigate by looking at the table directly in the ANSI standard. Okay? All right, that takes care of this example. We'll move on to the next one.